All right, in this video we are going to complete the correlation and regression practice lab. Here's the problem. Vivian is concerned about the amount of time her son spends playing violent video games. She notes his occasional aggressive attitudes and behaviors, and she attributes these to the video games. However, her son argues that playing the games allows him to express his anger virtually, which in turn makes him less aggressive in real life. Vivian begins to wonder if there really is a relationship, i.e. correlation, between the time spent playing violent video games and children's aggression. She decides to survey other parents. She asks them how many hours per week their child spends playing violent video games, and then asks them to rate their child's aggression on a scale of 1 to 10, 1 being the least aggressive, 10 being the most aggressive. Data for these 30 children are provided below. So what's going on here? We're looking at a possible correlation between two variables, time spent playing violent video games and aggression. The population of interest to children. We have a sample of 30 children from the community with data available to us here. And we have two competing theories. So Vivian's theory is that playing these video games provokes violent attitudes and behaviors and causes the son to be more aggressive. So she is theorizing that there is a positive relationship between, or hypothesizing, I should say, a positive relationship between hours spent playing violent video games and aggression. Now we have a competing theory presented by her son. He says, hey, I'm an angry kid, and I want to get that anger out. And when I play these video games, I get my anger out, I express my anger, and now it's out. And when I'm in real life, I'm going to be less violent, less aggressive. So he's theorizing that it actually reduces his aggression in real life. So he's hypothesizing a negative or an inverse correlation between the two variables. So mom's thinking when violent video game use goes up, aggression goes up, right? So if we were to graph this, here's mom's theory, right? So the time spent playing video games in hours, and then the aggression is hours go up, aggression goes up, right? This is mom's theory. The kid's theory is the opposite, right? He says, when I play these video games and I spend more and more time playing them, my level of aggression goes down. I get it out. So he's hypothesizing a negative or inverse relationship. Mom is hypothesizing a positive or direct relationship between these two variables. All right, so that's the situation. We're going to test this empirically. Now we have fabricated data for the purposes of this assignment. But if you're interested in this topic, I encourage you to conduct your own literature review and find out what the literature really has to say. Now, the goal of this analysis is to examine the relationship between time spent playing violent video games, hours, and children's aggression. All right, let's take a look. So Vivian suspects there will be a relationship between time spent playing video games and aggression. Now, note the wording, right? She just says there will be a relationship. She doesn't say it will be a positive relationship. Now, this is her original hypothesis, but her son brings up this opposing theory, this conflicting theory, and she's open-minded. She says, well, I kind of thought it was this way, but his idea makes sense too. So let's just see if there's any relationship at all. So this is not a directional hypothesis. She just thinks there will be some association, positive or negative, and she's open-minded to finding out which one it is. She's an objective researcher. Okay, just a relationship. Now, the null hypothesis in general is that there's no effect or no relationship. In a t-test situation, right, you're comparing two means. The null hypothesis, the null hypothesis is that there's no difference, right? The means are equal. There's no effect, I should say. Now here we're saying there's no correlation. That's the null hypothesis. The symbol for hypothesis is R or rho. Make that a little bit better here. Okay, so the null hypothesis is that R is 0. In other words, the correlation, right, R is symbol for correlation, the correlation between these two variables is nothing. The alternate hypothesis, and this is because this is a bidirectional hypothesis, it's not directional, is that it is not 0. So it's just an equal sign with a line through it. R does not equal 0, right? That means it could be positive, it could be negative, but it's just not 0. Okay, so null hypothesis, alternate hypothesis. Now we run a correlation test, we have to check out certain assumptions about the data. If the assumptions are not met, then we cannot have confidence in our result, in our statistic. 4 main assumptions we're going to take a look at. The first one is normality. So we have here, and I've already produced these for you to save time, we have 2 histograms, and these are histograms of each univariate distribution. So the first one is hours spent playing violent video games. This is just a histogram of that distribution by itself. So it looks like the number goes up to about 10. The range goes from about 0 to 10. So these kids over here, it looks like there are 3 kids, right here. Right. So in this column, there are 3 kids here who don't play violent video games at all. Okay. Right here, that's what this means. 3 kids that she talked to out of the 30, so 10%, they didn't play any violent video games. Maybe they were not interested, their parents didn't allow it, or they didn't know about it because the parents are reporting the data. Always keep these things in mind. This looks like maybe 1 hour right here, so 0, 1, 2, 3. So 1 hour, so 2 kids played 1 hour a week of violent video games. Only 1 kid played, looks like 6 hours. All the way over here, then we had 2 kids who were playing 10 hours a week of violent video games, right over here. And this is a normal curve superimposed over the data. And the purpose of this is to see how the actual distribution, the observed distribution, compares to a theoretical normal curve we have right here. Over here we have aggression level. This is measured on a scale of 1 to 10. It's fairly subjective. How aggressive is your kiddo? Again, we're using parent report data, so I always want to keep in mind there could be some reliability issues here. Maybe mom is unaware or is a little bit maybe overly optimistic about her child's behavior, or perhaps overly critical. There's actually some data that suggests that whether the ratings of a child's behavior come from mom or dad influence how problematic they think the behavior is. So mom and dad could rate the same kid, and mom says, oh, this kid is out of control. He's got all these bad behaviors. Dad says, he's just being a kid, just being a boy. And so he might rate it lower. So, we didn't account for all that. So always keep those things in mind. There's going to be some error. But here we have our histogram of the aggression levels. This is a 1, so 2 of the parents said their kids were, very non-aggressive. Over here we have 1 parent that rated their kid at a 10. So you got to wonder what's going on in that household. That the parent, how aggressive and violent is your child on a scale of 1 to 10? They say 10. My kid is kind of a little monster. So most of them are here in the middle. So what we're going to do is compare the observed distribution to these normal curves to see if they are, and here's the key, approximately normal. So we're never going to have a distribution, or virtually never have a distribution that is perfectly normal, that follows this curve exactly. But we're looking for something that is roughly along those lines. Okay, so we're looking out for an extreme skew. Okay, so here, this one kind of follows it fairly closely. This one, a lot of folks would see this little dip right here and think, oh, this really isn't normal. It deviates quite a bit. But actually, when we talk about approximately normal, this is pretty much okay. We're looking for really extreme deviations. So something like, imagine, I'll kind of draw it here. Imagine they kind of look like this, and they kind of came over here. And then maybe there's a bar here and one there, right? You kind of see my one I drew on top of that. That's clearly not a normal distribution. I mean, this is way over here. You got the skew on the left here, these tall bars on the side. This would not be an approximately normal distribution. However, these basically are. So we're looking for gross violations of these assumptions for the most part here. So describe the shape of these distributions. Has the assumption been met? So how would we state this? I'm going to go ahead and put a little text box here. I'll type this in. And I'm going to say that both variables are approximately normally distributed. There we go. So that's the keyword, approximately normally distributed. We're doing a rough visual inspection. We could even note that. A visual inspection of the histograms revealed that both variables were approximately normally distributed. So if we were writing this up in a study, we'd want to explain how we arrived at this conclusion. There are more technical ways of assessing normality. You could use some statistical tests. You could look at a PP plot, for example. Here we're just eyeballing it, and we're saying a visual inspection reveals that both are approximately normally distributed. In many cases, that is sufficient. If we started to see, before I was talking about what a non-normal distribution might look like, but if you were start to see something like that, you say, well, is it starting to veer over? You might want to use some of those other tests and explain how you came at your conclusion. But here, visual inspection, we're normally distributed. So what does that mean? So we'd say the assumption of normality has been met. There we go. That's all we need to say about that. We're going to go ahead and move on to the next assumption. The next assumption is homogeneity of variance, also known as homoskedasticity. And the idea here is that the variation and the dependent variable, the level of variation is roughly equal at each level of the independent variable. So this is one that students often have a hard time understanding and determining whether or not this assumption has been met. So before I actually plot the data, let's talk a little bit about what would look like for the assumption to be met, what it would look like for it not to be met. Now, her original hypothesis, Vivian's original hypothesis, was a direct correlation. So some sort of a line going up as you go to the right. So we're not expecting them to be level. If they were level, that would mean there was no correlation, right? There would not be evidence to reject the null hypothesis. We're expecting something to look kind of like this. So what you want to see is kind of an oval shape, right? Something like that. This is basically what homogeneity of variance would look like. And so at the very middle, we'd expect to have the most observations. So you'd have some data points along here. So assume this is the middle point. You're going to have a lot of observations here. As you go out, you're going to have less observations. As you go along here, both ends, less observations. So it's going to not be a rectangle, right? You're going to have less observations on the ends because they're simply less common. Right? There's not that many kids that are spending 10 hours a week playing violent video games, not that many playing no hours. Most are somewhere in the middle. In most cases, that's how the distribution works. And so you have kind of this oval shape. This is basically what we're looking for, something like this. So if you go up to the high end, you have some variability and aggression level, roughly the same level, roughly the same level. So we're looking for something that kind of looks like that. Now, what happens if we don't have this assumption met? What does that look like? So try to erase all these little dots here. Usually what you're going to see is some kind of what's called funneling. And that's going to look like this. So think of a funnel where it's wide on one end and narrow on the other. And what happens is you have not few observations. Let me clarify, not few observations on the narrow end, you have compact observations on the narrow end. And as it goes along, and it could be, the funnel could open up this way too, it doesn't matter which way. As you go out, they spread out. Right? So this is heteroskedasticity. So the variation is different. So what this would mean in this case is that kids who didn't spend very much time playing the violent video games all had roughly the same level of aggression, right? Why is this lit up? Who knows? I'll just go ahead. They all have roughly the same level of aggression over here. It's fairly compact. But the kids that are playing a lot of violent video games, you have a lot of variability in through here. Let's see if I can get rid of that little. There it goes. You have a lot of variability on this side. So if they don't play a lot of violent video games, you can predict their aggression level very well. If they do spend a lot of time playing these video games, it's very difficult to predict their aggression level. It could be low, it could be high. And what this would mean is that we have a model specification error. It means that we need another variable to explain this variation. Our variable that we have explains the variation on this end, but once you get over here, there's more to the story that we need to account for. And coming up with a single R statistic to summarize this entire relationship would be misleading. So that's why this assumption is important, and that's more or less what we're looking for, what we're looking not to have. So we go ahead and erase all these little dots. We're going to plot the actual data to see what they look like. All right, here we go. So to do this, I'm going to have to bring up the table side by side, and I'll show you how to plot these points. All right, here we go. So here are our data over here on the left. There are 30 observations, so 15 in the first table, 15 in the second half of the table over on this side. And for each kid, you have two pieces of information: the hours they spent playing the violent video games and their parent-rated parent report level of aggression. So we're going to graph these over here on this scatter plot. So the first in the first one here, we have 5 hours and 4 level 4 aggression. So I'm going to go down here and find 5 and go up here to 4. Okay, I'm going to draw a dot right there. I'll try to make it thick so it'll show up on your screen. There we go. So 5, 4. 5 hours of video games, level 4 aggression. Okay, next one, 3 hours, aggression 5. Okay, so 3 hours, aggression 5 right here, right in the middle of this circle. Okay, or this box, excuse me. So they spent 3 hours playing violent video games, and their aggression level was a 5. Next one is 4 hours, aggression level 2. Okay, so 4 hours is right here. Aggression level 2 is going to fall right there. Now we don't really have much of a sense of the shape of the distribution yet. That's of the relationship yet. That's why we need many data points in order to draw conclusions. Next one, hours 10, aggression 4, all the way over here. So this kid spent a lot of time playing these violent games. His aggression level, according to his parents, was a 4. Next one, 9 and 9. Okay, so 9 hours, aggression 9 is going to fall right here. There we go. 8 and 6, so 8 and 6. Hopefully this is now making sense to you what we're doing. And then 0 and 3, so no time spent playing these violent games, aggression level of a 3. And we have 1, 7, so they spend 1 hour playing the games. Aggression level is still on the higher end here. The next one spent 6 hours, side aggression 7, so that's going to fall right about here. Okay, and then 7, 3, 7 is here, 3 is going to be right in the middle. There we go. 4 and 1, 4 and 1 is going to fall right there. Okay, 5 and 6, right there. 7 and 8 is going to be right about there. And what else we have? 0 and 4, okay, that's going to be right there. There we go. And 9 and 5. Okay, so here are the first 15 data points listed here. We were going to graph the rest of them, but what do we see so far? Does it appear to be a positive, negative, no relationship? There's a lot of variability here. Kind of looks like maybe there's a little bit of a positive relationship, but they're not real tightly packed. There's still quite a bit of variation. So let's go ahead and graph the other 15 before we try to draw any conclusions. All right. So hours 3, aggression 2. So we'll keep on going about this. So hours 3, aggression 2 is going to be right there. Hours 8, aggression 8. Okay. That's going to fall right there. Hours 1, aggression 5. Hours 5, aggression 8. Right about there. Hours 4, aggression 1. Oh, so we have it's in the same place as another one. So I'm just going to kind of, I don't know here. It's going to let me do it. It wants me to make a comment or something. So I have a little trouble with that. That's just an artifact in my program I'm using. There we go. So I just kind of put them side by side so we can see visually that they're two kind of in that same place. 7 and 6. 7 and 6 will be right here. There we go. 7 and 10. It's going to land us right up here. 10 and 7. Go right there. What else we have? 2 and 2. Okay, right on this point. 8 and 6. Look, we have another one that's kind of on top of itself. So if it'll let me come in here. Oh, don't want to do that. Let's see if it'll let me come in here. There we go. If I can just add another dot next to it. Oh, easier said than done. There we go. Okay, that's 2. There we go. Let's see here. There we go. 8 and 6 make that bigger. 4 and 6 is going to put us right about there. And 2 and 3 will land here. 3 and 3 right there. 0 and 3. We have another 0, 3. So that is going to, see if I can sneak that in there. There we go. What else do we have? 4 and 4. So we go to 4 and up to 4. Here we go. So now we have a graph, a scatter plot of all the different data points, all 30 of them, and we can start to take a look and see what we see. Okay. So first we're going to be talking about homogeneity of variance here, but since we're at it, let's kind of take a look at the overall trend. Does it look like there's a positive slope, a negative slope, right? So does it go up? Does it go down? Or does it look like it's fairly level? Now, a lot of people look at this and see, man, this is so scattered out. There doesn't look like there's any correlation here at all. But it could just be a weaker correlation, which is what we might expect in a situation like this. Right? Even if there is a relationship between violent video games and level of aggression, it's not going to be the only thing that's predicting the child's aggression. Right? You have the child's temperament, you have the child's environment, a number of other things that could come into play. You know, they're whether or not they're active in a faith community, all sorts of things. So we're not expecting certainly to have a perfect or very, very strong correlation. So the question is the slope, if there is a slope, is it level? Does it go down? Does it go up? So here I would argue that this slope, there's what appears to be kind of a positive slope here. If you were to put a line through the middle of the data points, it would probably look something like that, right? That would be no relationship, and this would be an inverse relationship. So here, there appears to be a bit of a positive relationship. Now let's look at what the variability looks like relative to that line. So in the middle, you've got, let's see here, you've got about this much spread over on the high end, about that much spread down here, about that much spread. So what we see here is that the variability, the variance is roughly equal at each level of the independent variable of video games. So this is what we're looking for. So yes, homogeneity of variance, that assumption has been satisfied. For you to say that it's not, again, we're looking for a very egregious, a very dramatic violation of that. So it would need to look, so here again, remember we're saying we're kind of looking for an oval shape, right? So that's roughly our oval shape. For us to say that no, it's not, it would need to look, you know, something like this, really funnel shaped, right? And that's simply not what we have. So let's go ahead and indicate that here on our write-up. So we're going to say that the variation in the aggression variable, I'm having a lot of time with that, aren't I? Aggression variable. My keyboard's over to the side. I have my tablet over here to write on, so I'm at a funny angle, which is why I keep having trouble with these writing the words down. The variation in the aggression variable is roughly equal at each level of the violent video game variable, right? Therefore, the assumption of homogeneity of variance has been satisfied. Okay, so our first assumption was normality. We found that that's been satisfied. Our second assumption, homogeneity of variance, also been satisfied here. Let's go down and take a look at the next assumption, linearity. To assess for linearity, refer back to the scatter plot. Is the assumption of linearity supported? So let's talk about linearity. Okay. What do we mean by this? Well, even if you do have a relationship between two variables, it doesn't necessarily mean that it is a linear relationship. Okay? You could have a situation where the relationship is not linear. So I'll give you an example of what that might look like. So I'm going to draw what our scatter plot could be. So linear looks like this. It's a straight line. The data points are, let's see here. The data points are following basically a straight line. It could be straight, it could be up, it could be level, it could be up, it could be down, all of the above. but it doesn't have to necessarily follow a linear relationship. You could have what's called a curvilinear relationship or a parabolic relationship. So in the middle level of your independent variable, your dependent variable is high, right? When the independent variable goes up, it drops. When the independent variable goes down, it drops. It can look something like this. And a good example of a curvilinear relationship would be test anxiety and test performance. Okay, so here's what that means. When you go to take a test, you want to have some level of anxiety, some level of nervousness, because it's going to help you focus, it's going to keep you attentive, it's going to motivate you to study, it's going to keep you engaged. So you want like a moderate level of emotional investment in this test you're going to take. But if you are too anxious, right? So let's say this is anxiety on the X, and you're really anxious, you're so anxious, you can't even concentrate on the test. When you study, you're too distracted worrying about what's going to happen if I fail this test. Am I going to fail the class? Am I going to have to drop out of school? Am I going to live on the streets? And you can't even pay attention. Your performance, right? So let's say our dependent variable, or Y, is performance, test performance, is going to go down. Now it could go the other way. Let's say you don't care at all about this test. I have my grade in the bag. Even if I get a 0 on this test, I'm still going to ace this class, or I don't even need this class for graduation. I couldn't care less. You're not going to study, you're not going to pay attention, you might be thinking about what you're going to have for lunch, and your test performance is also going to go down. So this is a curvilinear relationship. So this is what we're checking for. We look over here, we can see, are the data points arranged in kind of a straight line, like so, or did they go up and then back down again, right? Or do they go down and then back up again? And so the pattern is going to need to be fairly distinctively curvilinear for us to kind of abandon this model and abandon this assumption, kind of like we see over here. In this case, this does appear to be a linear relationship, right? So don't get too caught up in one or two observations. You might look and say, well, this one kind of went down here. Maybe it is curvilinear, but the overall trend appears to be positive in a linear fashion. So we're going to go ahead and note that down here on our write-up. Okay, so the data points appear to rise in a linear fashion as, what are we talking about here? As video game use increases, the aggression also increases. The assumption of linearity is supported. There we go. Okay, so as video game use goes up, aggression goes up, appears to be a linear relationship rather than a curvilinear relationship. And it could even do some bizarre things. You might have a situation where it goes up and then back down and then up again. You could have all sorts of interesting forms it could take. Most of the time we're going to be modeling a linear relationship, but keep in mind these other relationships do exist in the behavioral sciences. Finally, the absence of outliers. We'll inspect the histogram and scatter plot for univariate and bivariate outliers. Are there any observations that appear to be problematic? So let's take a look at that, outliers. This is another thing that students have some trouble with. They're kind of eager to find violations, and so they'll see something small and sort of pronounce that the assumption has not been met, when really we're looking for fairly egregious violations of the assumptions. So first we're going to take a look for univariate outliers. Univariate meaning one variable. So within this variable just taken by itself, are there outliers? The way we'd identify an outlier is we have all the other observations lumped together, and then on the the histogram, you'd have the last one, or you'd have almost the last one. Then you'd have a white space, and then you'd have another one over here, like that. Okay, this is what a univariate outlier would look like on a histogram. Everyone's over here, then there's a white space gap, and then you have an observation, and it could be to either side. It could be on this side, right, on the low end, or it could be on the high end. If we saw something like that, we would say there is a potential outlier. Okay. Get rid of those because that's not what we have. Over here, we're looking for the same thing. We would be looking for something kind of hanging out. It could be more than one. You could have a situation, suppose you had something like this, and there's a couple over here hanging out over here on the side. We would want to make note of this because this could create an issue. If you have that there, it is going to bias, potentially bias or weight your conclusions in one direction. Those observations are going to have more influence over the R coefficient than the other ones are, and that could be an issue potentially. So we're going to look out for that. But here we don't see any univariate outliers. There's nothing over here on the end. There's no gaps. So we don't need to worry about that. Another note I'll make while we're at it, even if there is a gap, it doesn't mean there's a problem, right? So if we had, let's say we had an observation right here, okay? If you were to look at your normal curve, it's kind of right on that curve. So even though there is a space here, okay, even though there's a space here, it doesn't mean that this is an outlier. It would need to be further over. Now, it wouldn't make sense in this case. We're not playing negative hours. So let's say we have 9 hours, 10 hours, and then some kid was playing, I don't know, 13 hours, wherever this puts us over here. So no one played 11, no one played 12, but then somebody was playing 13. Again, it's still on this normal curve. I wouldn't necessarily call that an outlier. It still seems like it's not too unusual in light of the other observations. But if you had one way, for this graph, way over on this side, 20 hours or something way over there, this is unusual. And this observation is something we may need to pay special attention to. So no univariate outliers. What is a bivariate outlier? Remember, it asks us to look for univariate, right? Univariate and bivariate outliers. To look for a bivariate outlier, bivariate meaning two variables, this is an observation that is unusual in light of the other variable. So this is a different idea. You could have the same observation, which is not a univariate outlier, but could be a bivariate outlier. Okay? So that would be something that bucks the trend. So if we see a general positive relationship here, as violent video game use goes up, aggression goes up, but we have somebody, let's say there was somebody right here. All right, imagine this were a part of our data set. They play 10 hours of violent video games, but their aggression level is a 0. I think the lowest one was actually a 1, so it'd have to be up here. But you get the idea. Right? We'd say, by itself, having 10 hours of video games, that's not unusual, right? Other people played 10 hours of video games. Nothing weird about that. And having an aggression level of 10, also not that unusual. Other kids had an aggression level of 10. But the combination of having high video game use, aggression level of 0, aggression level of it'd have to be 1, right? It only goes to 1. So low aggression is not unusual. High video game use is not unusual. But putting both of those together in the same data set, let me correct that, it would be right about here. Putting both of those in the same data set together starts to make this observation potentially unusual. Another example would be if we had a no violent video game use, they didn't play any, but their aggression was a 10. So here's the trend right here. This one's bucking that trend. We have a potential bivariate outlier. And this is going to have a big influence on our coefficient because it's going to kind of pull this line. Right? So if this point were here, instead of the line being there, it might kind of, let's see here, it might kind of pull it this way. Right? So it's pulling the line towards that data point, like so. And having a lot more influence than adding a point here or a point here would. Let's get rid of all that. Don't want to confuse you. So we're looking for a univariate and bivariate outliers. They can bias our results. They can have undue influence on the statistics. We want to be wary of those. But we don't have those in this case. So no apparent univariate or bivariate outliers. So we'll make a note of that on our write-up. So we'll say let me go back over here. A visual inspection of the histograms and scatter plot revealed no apparent univariate or bivariate outliers. So I'm using the word no apparent outliers because we're doing this informally. It's an informal inspection, visual inspection. We aren't using, in this case, some sort of technical criteria, which you could, and many people do and would. They would perhaps over here, they could use, up here they could use z-scores. Also here you could use what are called residuals, standardized residuals, through a regression analysis to see how unusual a particular case is. So you could go about that in a technical way, but here we are, we're just using a visual inspection. I want to focus on the concepts. I want you to come out of this lab, these lab assignments, feeling like you get the basic idea, you can talk about it without getting too technical at this point in the process. Okay, moving forward, now that all of, we need to say that the assumption of absence of outliers is supported. There we go. So all three assumptions are supported or satisfied, have been supported or satisfied. Therefore, we can move on to evaluating the correlation coefficient. And it's important to go through these steps. Checking assumptions can be a little bit tedious. It's not the most fun, and it takes some time. What people often do is put a whole bunch of variables into a correlation analysis and then come up with a big table that has lots and lots, and they run around and find the ones that are significant and want to jump right on those. But that's not a great way to go about it, because if you don't check the assumptions, the coefficients you're looking at could be very misleading. Okay, evaluating the correlation coefficient. Using SPSS, so apparently Vivian has SPSS at home, good for her. She calculated the Pearson correlation coefficient for the relationship between time spent playing violent video games and aggression. The output is below. So all this information, all these data are now in the computer, in Vivian's computer, and the assumptions have been met, and it spits out a correlation coefficient. So let's take a look at this. So this is a correlation table. I want you to be very comfortable interpreting SPSS output so that when you use SPSS or a similar program, you'll be able to make sense out of it. Correlation tables are symmetrical. Okay? In this case, there are only two variables, right? So there's really only one coefficient being reported. But because these are symmetrical, you have identical data here and then below the axis. If we had more variables in our table, this would continue, and again, you would see symmetrical output. So you don't need to look, don't get confused, you don't need to look on both sides of this diagonal here. You can simply look at the top or the bottom to find the information that you're looking for. So let's talk about how to make sense out of this. So this cell, get rid of that line there. So this cell right here contains the information that we're interested in. Over here on the diagonal, we have the sample size, and we have the correlation between video games and video games. So it's the correlation of the variable with itself. Of course, it's 1. Everything has a perfect correlation with itself. So this is not terribly useful or informative. Really, all this is telling us is that 30 observations, 30 kids had data on the video game variable. Down here, this is the correlation between aggression and aggression, also 1. 30 kids had data on aggression. Because there are no missing data, the sample size is the same in every cell, 30, 30, 30, 30. You could have a situation where you had missing data. Maybe you knew this kid played 3 hours of games, but you didn't know his aggression level for some reason. Mom said, "That's none of your business. I'm not going to tell you. All I'll tell you is he plays 3 hours of games." It would not be helpful for analysis, but if this were the case, what would happen here is your aggression variable would have 29 right here, 29 right here, and where's the aggression? And 29 right here. So the numbers would not match because there would be 30 video game scores, but only 29 aggression scores, and we wouldn't be able to run the correlation for this observation. So we'd have what's called list-wise deletion. The computer would say, well, I'm just going to forget about this one and only run the correlation with the remaining 29 observations. So that's what would happen in that situation. But fortunately for us, it's a good day and there are no missing data. So sample size is on this last row right here. Let's look at the top row. So this is what we're interested in. The correlation coefficient, or R, is 0.494. 0.494. That is our correlation. A 1 is a perfect correlation. That would be a correlation of a variable with itself, or a correlation between two variables where there is no error. So if you were to look at the correlation between inches and feet, or between meters and kilometers, you would have no error. They are perfectly correlated. It would be a correlation of 1. 0 means no correlation at all. So this is going to be somewhere in the middle. we have a moderate level of correlation between these variables, 0.494. And there are different criteria for interpreting that, how large the correlation is. So there's three things that we want to look at when interpreting a correlation coefficient. You want to look at the direction, size, and significance of the correlation. I should say direction, size, and statistical significance. We could talk about the practical significance, the effect size, and that would be what I'm referring to as size. So first, the direction. Is it positive or negative? Right? So is this a positive 0.49 or a negative 0.49? Well, clearly it's not negative. It's positive. That means it is a direct correlation, not an indirect correlation. So our estimation here that there was a positive slope is supported by our correlation analysis. There is a positive or direct correlation between these variables. Again, these are made-up data, so if you're interested in this research question, I would encourage you to do a little review on your own. So that's what that means, though that addresses that question. But to address it further, is the correlation substantively significant? How big is it? So in this case, it is 0.49, right? Say moderate correlation. And then we look at the statistical significance. So SPSS is very nice. It gives us little stars right here. Let's try to move that around. So look right up here. There's these two little asterisks, or two little stars. And what this means, when you see this, is the correlation is significant at the 0.01 level. So P is less than 0.01. Usually 1 star means that P is less than 0.05. 2 stars, P is less than 0.01. Sometimes you'll even see 3 stars, right? And that means P is less than 0.001. So the more stars, the lower the p-value, the more significant the correlation. This should correspond to what we have in the next column, next row, the significance level. So significance is the same as the p-value, 0.005. So 0.005 is less than 0.01. It's not less than 0.001, but it's less than 0.01. That's the next cutoff level. So we have a positive, a moderate, positive, or moderate direct, statistically significant correlation between these variables. Okay, so we're going to break this down. What is the direction of the correlation? What does this mean? So the direction means, is it positive or negative? Does it go up or down, direct or inverse? As we saw from our scatter plot, right? And more importantly, our statistical test, we see that there is a positive correlation. Okay. Let me pop on that there. There we go. There is a positive or direct, so just two different ways of saying it, correlation between hours spent playing violent video games and aggression. This means that as time spent goes up, so does aggression. As time spent goes down, aggression goes down. In other words, kids who spend more time playing violent video games are more aggressive than those who spend less time playing violent video games. So I elaborated there a little bit to really make the point, but I think it's helpful to put it in common terms to make sense out of these numbers. So all we've interpreted right there is just the direction of the correlation, the fact that this coefficient is positive and not negative. Compare the correlation coefficient to the scatter plot you created. Are the two consistent? Okay, so let's see here. We look at the scatter plot. The data points appear to rise, right? There appears to be a positive slope, and we have a positive coefficient. So yes, they're consistent. If you were to find the opposite, let's suppose this were a negative coefficient right here, and yet the slope really appeared to be positive, I would be suspicious. I would wonder what's happening. Did I make a mistake somewhere? What's going on? So it's always good to do a reality check and make sure the numbers you're getting, look like the data and that they make sense. Okay, so let's go ahead and say something about that. The correlation coefficient is consistent with the scatter plot. In the scatter plot, the data points appear to rise, and the coefficient is positive. Okay, so this makes sense. They're consistent. They're both representing a positive relationship. Okay, both indicate a direct correlation or a positive relationship between the two variables. There we go. Is the correlation statistically significant? Okay. Well, how do we know? Is it, and how do we know? So when we talk about statistical significance, and this is very important, you're going to do this a lot. This needs to make sense to you. So if it doesn't, study up on this, continue to look into it in depth until it makes sense to you. Statistical significance, we're looking for that magic p is less than 0.05. So p is less than 0.01 is more significant. 0.001 would be more so than that. So, but as long as it's under 0.05, this value right here, we're dealing with statistical significance. So you're looking right there. Nope, not right there. Here we go. We're looking right there. Is this less than 0.05? That is the big question. And in fact, it is. 0.005 is less than 0.05, therefore it is statistically significant. Okay, so let's make a note of that. The significance level of the correlation was 0.005. Because this value is less than 0.05, so this is 5 thousandths, and 5 thousandths is less than 5 hundredths. Because this value is less than 0.05, we can say that the correlation is statistically significant at p is less than 0.01, in fact, right? Because it's less than 0.01. Okay, so I'll just kind of answer the question directly though. Is it statistically significant? Yes, it is. It's less than 0.05. It's actually even less than 0.01, but because it's less than 0.05, it is statistically significant. So you want to make sure you make that connection. When you interpret this table, you know how to make sense out of that. So it is a positive correlation. As hours go up, aggression goes up. And it is, let's see, I could probably get rid of this. And it is, make this a little bit bigger for you. There we go. So it's a positive correlation. It is a statistically significant correlation. And the last thing we want to know is whether it is a substantively significant correlation. In other words, is it a large, small, medium, weak correlation? The correlation is a function of, the significance of the correlation is a function of sample size. The more data points you have, the easier it is to find statistical significance, even if it's a small relationship, a small correlation, a weak correlation. So if we had 30,000 kids in our sample, pretty much any correlation is going to be statistically significant because the sample size is so large, and that's the way the formula for the significance works. So we need to make sure that the correlation is big enough to actually matter, and we're not, and make sure we're not just overstating a very small relationship just based on the statistical significance. So a correlation coefficient of 0.10 is thought to represent a weak or small association. Okay, so if this were 0.10, I'm talking about the correlation coefficient right up here. If this were 0.10, don't get these mixed up. If this were 0.10, we'd say it is a small correlation. It's very weak. Maybe we don't really care about that. Okay. Let's see here. What else? A 0.3 is moderate in that range, and then 0.5 or larger is a strong or a large correlation. So given these criteria, determine whether the correlation is practically significant. So we're in the 0.4, well, 0.49 range actually. So we're in the kind of the moderate to strong correlation range. So if 0.5 is kind of the cutoff to a strong correlation, we're just below that. So moderate to strong correlation. So that is substantively significant. The effect size is big. So there is a meaningful, statistically significant positive correlation between these two variables in our practice lab. Okay, so let's go ahead and make a note of that. Okay, the size of the correlation is 0.49 based on these criteria. This represents a moderate to strong correlation. It is substantively significant. So it is practically or substantively significant based on how big the correlation is. 0.49 is super close to this cutoff for a large correlation. It is statistically significant, and it is a direct or positive relationship. So this is what this information tells us from the table. So we want to make sure we're very comfortable interpreting these tables and making sense out of it. People will commonly mix these up, students, when they're first learning. Oftentimes, if the correlation is very small. If the correlation itself in a situation could be, let's say, 0.02. And they'll look at that and they're expecting a big correlation, just their hypothesis doesn't pan out. And so their brain gets mixed up and they think, well, it can't be that that correlation is so low. So what could happen, it could look like this. You could have a situation where the correlation is 0.02 and the p-value is 0.59, let's say, right? Based on depending on the sample size. So they switch these, right? So what's really going on is there's no relationship and the significance is super low, i.e. a high p-value, high significance level. So there's nothing going on here, right? So if this were the correlation and this were the p-value, there's just nothing. There's no relationship. But they're expecting one, so they start to switch these in their heads and say that, oh, there's a strong, highly significant relationship here. So make sure you pay close attention to which part of the table you're interpreting to make sure you interpret that correctly. Okay, so interpret the correlation coefficient. Okay. Based on these results, should she reject or fail to reject the null hypothesis? Explain. Let's go back to our hypotheses. Right up here. The null hypothesis is that the correlation is 0. Do we have enough evidence to reject this hypothesis? Well, according to our analysis, there is less than a 0.5% chance, so less than a 1% chance. There's a 5%, so there's a 0.5%, so there's less than a 1% chance that we would generate a test statistic this large, 0.49, if the null hypothesis were true. Right? If there really is no relationship, it's very unlikely we would have gotten these results. So it's very unlikely that this is true. Very, very unlikely based on the data we got. So we have enough evidence to reject this hypothesis in favor of the alternate hypothesis. So we have evidence for evidence we need to reject this and say we don't know for sure, but it really appears that there is with high probability a relationship between these variables based on the data in front of us. Okay, so let's go ahead and write that down. There is less than a 1% chance, that's that p is less than 0.01, that we would generate a test statistic at least this large. It was r equals 0.49 if the null hypothesis, which is that there is no relationship between the variables in the population, were true. Therefore, we will reject the null hypothesis in favor of the alternate hypothesis. There we go. Now, people think, why don't we just accept the alternate hypothesis? It's a very convoluted way of saying that, right? Why don't we just say we accept the alternate, that there is a relationship? Because we're never proving that there is a relationship in the population. We're just determining how likely it is that there's not a relationship. So we're always dealing with probability. We're making inferences. We haven't proven something, but we're making inferences about what the relationship might be. Let's take a look at the next question. Do these results prove Now, always be suspicious. Whenever we're talking about study, science, experiments, be very wary of the word prove. When you see somebody, a news article talking about a new scientific study proves that such and such, they probably don't know what they're talking about, and they're probably overstating the results. Right? We usually use the language suggests or indicates or provides evidence in favor of the theory that, but we very seldom say that something proves something. We're usually very cautious with that word. So whenever you see prove, that should be a red flag. I could even draw a red flag. Okay. Whenever you see the word proves, that's a red flag. We don't know for sure it's a problem, but be careful for that. That violent video game use increases aggression in children. So there's a couple of issues here. First of all, the word prove, be leery. That violent video game use increases aggression in children. So we've established that there appears to be a relationship between the two. We got that far. But does it mean that the video game use causes the aggression? So here we're dealing with, so here's the key issue that we're trying to focus on in this question. Does correlation imply causation? Just because the two are correlated, as one goes up, the other goes up, does that mean that this one is causing that one? No, that's the theory that the mom is starting with, and even the son has that theory. He just thinks that's a negative relationship, but just because they're related to each other doesn't mean one's causing the other one. We have not established that. In order to establish causation, well, there's a few ways you can kind of go about it with a correlational study like this, but you would need a lot more information to work with. But traditionally, the best way to establish causation is by using an experimental design, where you actually manipulate the variable and see what happens. So you would have to get kids to play different amounts of violent video games and then see what happens. Right? Then you could start to get a sense for a causal relationship. But here, it's strictly correlational. We collected data on these two outcomes, and we don't know that one's causing the other. Could be the other way around, right? You could flip the axes and put aggression on the X and video games on the Y, and you could make a case that aggressive kids just like violent video games. Right, so it's not that the games are making them aggressive. It's just that you have this aggressive kid, and they're looking for what to play, and they don't want to play, they don't want to play some peaceful game. They, a puzzle game or something. They want to go attack and shoot people. Right. There also could be some tertiary variable that's producing both of these. Maybe there's some violence in their lives. Maybe there's some unstable home situation. They're not being supervised or cared for properly, which means they have kind of free reign to play whatever they want, so they're making questionable choices about their entertainment, and creating aggression in them, because there's maybe some environmental problems. So we don't know for sure that this is causing this. That's our theory. We know they're related, but we don't know that there's necessarily a causal relationship. So be very careful when you see the word prove. And also be careful when they're using causal language. It increases or causes aggression. Okay, so we're going to say here, our results indicate that there is a relationship between these two variables. However, this is a correlational study, although the results are consistent with this causal theory, we have not established causality. Okay. So no, the results do not prove that video game use increases or causes aggression. Okay, so we have to be very careful with our findings. Now notice what we said here, it's consistent with this causal theory. So a lot of times we look to see if the data support a theory or are consistent with the theory. So let's look at that right here. Vivian's son claims that playing violent video games allows him to express his anger, which makes him less aggressive in real life. Do these findings disprove his theory? Okay, so his theory is that it brings down aggression. Okay. So we said that we can't prove that it makes the aggression go up. did we prove that it doesn't make aggression go down? So we can't say for sure. In other words, we can't say for sure that mom is right. Can we say for sure that son is wrong? Interesting. Well, if she's right, we know there's going to be a positive relationship. We know that the correlation is going to be is going to look like this, right? Go move up from left to right. Now there could be other reasons that could happen other than her theory, but that's sort of a necessary condition for her theory to be right. Now his theory is that they're going to, that it reduces aggression. So if he's right, there should be an inverse relationship observed. Now if we had seen an inverse relationship, it still wouldn't prove that he was right, but it would at least allow us to continue believing that. So here the situation's a little bit different, because if he's right, this would need to look different. The data would need to look differently. So with a little more confidence, we can say that the findings really do not support his theory, okay? Because it would need to be an inverse relationship for that to be the case, okay? In this study, we observed a positive relationship between violent video game use and aggression. If her son's theory were correct, we should have observed an inverse or negative relationship. Therefore, the data do not support, or they are inconsistent with, her son's theory. Okay. Now, I still kind of cautiously, sneakily avoided the disprove language. We're still making inferences. There could be, there's still a chance that the relationship looks different. It's very small. It's less than 1%. But there's a possibility that he's right, and there's just something quirky about these data. There's some variable that we haven't taken into consideration. We talked to, his friend's parents, but maybe there's something different going on with him. He's the exception to the rule. Remember that there are some, kind of rough outliers here. This one spent a lot of time playing video games, but the aggression level still appears to be more or less below average. So we haven't proven the kid wrong. Maybe for him, maybe just him, maybe he's the only exception. Maybe something different is going on. Maybe it does help him in some way, but they certainly, the data certainly do not support his theory, at least in general. Okay. All right. Moving forward, we're going to I'll go ahead and make a separate video talking about the next part of this lab, where we run a simple linear regression. We consider that it's an extension of correlation, but we have to look at some additional information and make predictions. So we'll go ahead and I'll put that in the next video.